So as it was introduced, I'm going to talk about scalable user verbs for a shared memory. This slide deck was prepared by a few of my colleagues. There is Avnish and Sumanta. They are sitting in the audience, and also few folks back, including Amar. I'll try to run through the slides, and in the end, Avnish and Sumanta will join me for any Q&A which you may have. So before I talk about verbs, the new verbs or whatever verbs we are using, it will be only appropriate to talk about what are the shortcomings, what are the pitfalls of the existing memory verbs. I'll try to talk about why we ended up developing additional verbs, how we use it, some mechanics about the APIs. While doing this, because we have been using this API for a while, we also found a lot more opportunities to even further improve this and take it to the next level. So I'll talk about a little bit of that, and hopefully end of the slides we'll be able to convey the genericness of this API and see what can be done to get these in standard verbs or at least some sort of extensions. We added few introductory slides. They talk about the Oracle database process and memory architecture. These slides we have put just to give you an idea how the mechanics are, and I hope that that introduction will just give you which will help you to visualize how this API is being used and why they are useful for Oracle databases. So in databases we have something called Oracle process. Oracle process is the execution entity. It's basically a runtime instantiation of database code which is executing on behalf of the client request and various background tasks which are doing bookkeeping for the databases. Oracle process is not always OS process. OS is an operating system process. It can be a OS process on most of the Unix platforms. It can be a OS thread. This is default on Windows. It can be a user thread or a fiber which is available on Windows. There are broadly two categories of Oracle processes. We call them background and foregrounds. Foregrounds are basically the DB server processes which are spawned on behalf of servicing the clients, and backgrounds are basically you can some sort of call them as bookkeeping processes for the database server, which keep running in background, and hence the name background. Taking a snapshot of a database instance and various memories associated with it. So as I said, Oracle instance is basically a collection of processes attached to a shared memory. All processes in the shared memory model map the memory symmetrically. Majority of the processes, majority of the memory is basically used for the buffer cache. In fact, 90% of the memory, 80 to 90% of the memory based on the profile is used for the DB blocks. Rest of the memory is spread into various pools. Under pressure, this memory can be moved from pools to pool, and we want to do RDMA from any process to any other process over this shared memory. Just give you the perspective, the scale of the scale is very important. We are talking really order of magnitude of processes. It can be from the 20,000 processes to 100,000 plus processes, and gigabytes to terabytes of shared memory. So scale is very important. Quickly running through the process model, there are 3 process model. I'll talk about it, and don't ask me why is this and why is that, but Oracle provides supports all of them because customer wants to use in a different ways. So this is a classic model where operating system process is a Oracle process, and it's a 1:1 model. We call it classic model. Then we have this single process multi-thread model where all the Oracle processes are like threads running in a single container process. This is what Windows does. And we also support something called a multi-process, multi-threaded model where group of threads, Oracle processes running under a OS process. So with that brief introduction, let's get into the actual use case I wanted to talk about and give some perspective from our side. So as I said, the scale is really, really important. Imagine you want to register a memory to a HCA and using standard IB reg MR, if you have to do that for 100,000 processes, you will be forever just doing memory registration. So that's definitely a no-no. It impacts multiple things, but also puts a lot of pressure in the real execution state on some of the HCA resources. We'll talk about that in a bit. So the idea is very simple. In fact, this API is really a software construct. Conceptually, we'll have an init processor, which is typically a fatal process, registers the entire memory to the HCA on behalf of all the processes, stores the handle in the shared memory, and all the other processes use this shared PD handle. Mind you, every process has its own QPs and connections and all the resources. The key idea is really to reuse the memory mappings and avoid the translation cost. It's actually interesting. I didn't envision this, but we just had a ODP session which was talking all about that. So so it's very important, and you'll see some of the data later how it impacts this translation cost to the actual workloads. The PD, which is allocated as part of shared PD, is valid as long as there is one process attached to it. So that's like a lifetime of PD on an Oracle database. Drilling further down, just talking about the APIs, I had a slide with code, and Sumanta suggested me that instead of code, you just have a very simplified side, and I do agree it helps. So basically, init process, as I said, or let's say in this case, what slide says is a process A allocates a PD using IB alloc PD, and mark this allocated PD as a shareable using a verb extension. We call it IB alloc shared PD. It's basically putting a reference count on this PD and getting a shared PD handle. You store this handle in the shared memory, and then the actual processes which wants to do RDMA take this handle, call IBV shared PD, pass the handle to the IBV shared PD, which will get you access to the actual hardware PD, and then you those processes will use that PD to associate and allocate all the IB resources what it needs to. It's a small structure with the SHPD handle.
Yeah, is it just an integer or just some
number?
No,
it's a structure with 3 fields, and I don't know whether it's there on the last backup slide. No, it's a structure. It has a couple of keys. Yes.
So I think if you want that upstream, that's probably going to have to be a file descriptor.
Okay. Okay. Like XRC, you mean? Okay. Okay. So thanks, Jason. So we thought to demonstrate, why do we need this API, we should have some data to share, and thanks to our performance team, we got some data to share with you. This data is generated using database cache fusion use case. And the use case is a bit complex, but we try to really capture the data which makes sense, and it's a slightly simplified view of the actual use case. So it's a typical server client model. One of the node is running the LMS servers. LMS is basically our cache services, global cache services, where clients can request the database blocks and the LMS service is there. So 30 servers we are running on one of the node, and other node is running clients. We did a couple of runs. One was with 100 clients and another one was with 2,000 clients. Just to avoid the noise on the I/O side, we kept the memory minimum on the client side to 1 gigabytes and have a larger, not really larger, but okay, 100 GB SGA on the server side. The fabric what we use, or the network what we use, is InfiniBand with Mellanox CX3 HCAs. I specifically mentioned that because some of the terminologies on the 2 slides later talk about something called MPTs and MTTs. These are Mellanox implementation of translation tables. You can view them as TLBs, similar to processor TLBs. So there are a couple of graphs here. The first bar graph is basically the receive time. It's basically a total round trip time to fetch a block from a remote node. That also includes processing, CPU processing. And the second graph is basically total cluster wait time to do a full network I/O. The bars in the blue color, is it blue? Yeah. So blue color basically represent the numbers without shared PD API usage, and the one in green represent one with shared PD. As you can see, with small number of clients, let's say 100 clients, you hardly see any difference. I mean, they are very comparable, but once you scale the clients, in case you see 2,000 clients, there is a massive saving which directly application sees. I mean, this is not some micro benchmark, but this is a saving at the application database level, where total round trip time and total network I/O time has gone down by 50%. And it goes without saying, this trend continues, and for larger scale, these numbers even start showing more impressive numbers. Zooming into the HCA, as I said, right, I mean, these are really internal HCA statistics. What we are plotting here is the protection table translations and memory table translation stats. It's basically misses per seconds. There are 4 graphs there. So basically, it's plotting on the server side and client side as well. So the MPT misses on the server, MPT misses on the clients, MTT misses on the server, and MTT misses on the client. So you can really see how massive impact it has on the MPT miss rates. I mean, with the shared PD, as I said, the green graphs are with shared PD and bars. So with shared PD, you can see almost 2.5 to 3x MTT usage. MPT usage goes down. MTT is 20% reduction, and I'll talk about it actually. We know also what's going on here, and that's why I was saying there is a further scope to improve this. And we have also seen how it benefits directly from the previous slides when once you optimize this part, how it benefits the application. So continuing the theme on the shared shared PD, we were also thinking of a verb called shared MR, or a contig MR might be more appropriate, which can help us to reduce those MTTs. At one point of time, Mellnox Ofed floated a couple of experimental verbs. They were called regMR and experimental regMR and shared MR. But I guess they were dropped later. I happened to follow that discussion on the mailing list as well. I guess the API itself, nobody had problem, but it was really the implementation, because memory management and the RDMA resource management are two separate subsystems, and nobody wanted to mix them together, which is understandable, but I guess the benefit is still there. So at least our view, our idea behind this API was to basically allocate and register a contiguous memory using a shared PD, and then attach this allocated memory in one to another process using shared PD, and then do a direct I/O. And the intention was really not to duplicate registrations, take a cost of keys and MTTs and all of it. Well, it goes without saying, this also means you have to map the memory symmetrically across processes, and that's how Oracle anyway maps it, so it's fine with us. There are a couple of further use cases we have been exploring. One was really we talked about all shared memory. We're also thinking about the process private heaps coming out of a large MR, and these heaps are like blocks of memory, part of this large MR. I don't know that I mentioned, but all this memory is backed by huge pages. So we do understand advantage of huge pages and TLBs and all of that. So that's already part of the game. And this private heap, which we will register, and then if the Oracle process dies, that memory will be claimed by this heap manager and given to another process. That way, we don't have to keep mapping again, and that save the translation cost. Another interesting use case was building a proxy communication models. So this is basically to take care of scaling issues at the server, where you have a server, let's say an NFS server servicing thousands of clients, basically, and then every process is trying to connect to that server and then asking for the to do RDMA into its space. Instead of doing that, if you have this pool of memory which can be made available to a thread pool kind of a background worker, then that can actually talk to that server, and that way not overburden the server, but still get the job done. And of course, it goes without saying, this thread pool will have access to this memory and keys from the processes. There is also an interesting use case with SPDK. I'm not sure how many of you have been following it, but it's a storage development toolkit which built on top of DBTK. And when you are using for the storage initiators, there can be many initiators, and if you have such a pool, you can again share the memory mapping and registration across all the initiators, and reap the benefits what we already talked about. So yeah, I think that's it. I'll just try to summarize again. Shared memory is really a common use case. I don't think Oracle is the only one who uses shared memory. And these verbs definitely improve scaling issues for shared memory. As I said, it's a software construct, and the API itself are very generic. They are hardware agnostic, vendor independent, and we think it would benefit larger RDMA technologies. Not just InfiniBand. We have been shipping this in InfiniBand stack and also testing with Rocky. We have a session on Rocky tomorrow. We really believe that these are good candidates to be included in standard verbs. If not standard verbs, at least some sort of extensions. So with that, I stop and take your questions.